Now there's a fifth thing I forgot to say on the last video when I was going over the four things that you should do to, increase your yield. The fifth thing is the speed of the ethanol traveling over the catalyst. In the video, I do it very slow. I have the pot at a simmer. It's not even really boiling. It's just evaporating off almost pretty much. That is not correct. You should do it fast. I don't know how you can do it as fast as these people are doing it in their papers without it being too dangerous. Because they're doing like 500 milliliters a minute through the catalyst. It's like, that's ridiculous. So you should do it as fast as you can without, having too much pressure build up in there. You know what I'm saying? That's all I can say about that. Okay, now let's talk about this catalyst support structure, okay? Two main ones I'm talking about is silica and alumina. And when I say silica, I mean silica gel, and when I say alumina, I mean gamma alumina. You should have between 0.01 to 5% by weight of metal compared to the catalyst support, okay? And let's go on how to make gamma alumina. Now keep in mind, I've never made gamma alumina, and even if I did, I wouldn't know how to test it to make sure it was, well, yeah, I guess I do know how to test it. You test it by measuring the pore volume by water titration, and I'll get into that later. But here's a couple equations that you can see that make gamma alumina. This first one I got from Wikipedia. Just take some aluminum sulfate and heat it up to 580 to 900 C. You make gamma alumina. The only bad thing is you also make sulfur trioxide, which is nasty. And if you put it into water, like you try to bubble it through water to make sulfuric acid, it's really exothermic. I would not do that. Maybe if you have a fan, like a fume hood, that'd be good, I guess. But if you can lead it into maybe some empty vessels that have just a couple mils of water in it, you know what I mean, and put that in ice, on an ice bath, maybe, you could do that. But anyways, this next one, I have no clue where I got it from. I can't remember. Take some alpha alumina, just basic alumina that you buy anywhere. Heat it at 1,000 degrees Celsius for 2 hours. Apparently you'll make gamma alumina. Take aluminum trioxide and heat it at 800 C for 4 hours, taking the first 2 hours just to get up to temp. You know what I mean? And then the next 2 hours, leave it at 800 C. You'll make gamma alumina. Another one, I don't know where I got this at. Amorphous alumina. Take it, heat it to 500 C, and you'll make gamma alumina. And the last one is the same as this one, is the same as this one, but it's got a different temp there, you can see. Take aluminum trioxide, take it greater than 1,100 C, and you will make gamma alumina plus water. Now when I read that last one, it also, I think I got that from Wikipedia too. It says that the gamma alumina you make tends to be multi-phase, so it's not going to all be gamma alumina. It's going to be a mixture of gamma alumina with other metaphase structures of alumina, okay? So this up here that says 800 C, that probably does the same thing. It probably makes a multi-phase gamma alumina, alpha alumina, beta alumina, gamma, theta, whatever, a bunch of mixtures of the phase. But as long as you can make at least some of it, it'd be good. But like I said, if you use alumina as your gamma alumina as your support structure, your catalyst support structure, it will not only act as a support structure, but it will also act as a catalyst, making more byproducts that you do not want, okay? The silica dioxide is probably the better deal. Now, how do you get the metal onto the structure, onto the gamma alumina? Well, let's see. Well, you do an incipient wetness impregnation. Okay, first you measure the pore volume by H2O titration. What I mean by that is take a small portion and weigh it up like a half a gram and put it in a cup, and then drip by drip add water to it, keeping track of how much water you're adding, right? And once the alumina is wet as it can be, all of it, you stir it up, you know what I mean? But you don't want any excess water in there, okay? You want to be able to pick up the alumina and there not be any water, you know, in the cup. Just enough to cover it all up. And that will tell you, let's say you have a half a gram of alumina, and you end up putting a half a milliliter of water on it before it becomes saturated. That means you got 1 milliliter of water per 1 gram of alumina. And remember, when you do this, you got to dry your alumina out first. You know what I mean? Put it in the oven for 24 hours at 110 C, or if you want to put it in the oven less, you know, raise the temp up to maybe 150 C or something. You know what I mean? But you want your alumina really dry. You know what I mean? So that you know how much water you're putting in is how much water you're putting in, and no other extra water. So anyways, you got, let's say you need 20 grams of alumina to fill out the volume you want in your tube furnace. So now you know, get some more dry alumina, 20 grams if that's what you want, and you know now you need 20 milliliters to totally saturate it, right? So what you're going to do is you're going to take less than 20 milliliters, right? You're going to dissolve your metal nitrate in that appropriate amount of water, right? Which you want to start under 20 mils, and when let's say you're using copper, you'd put copper nitrate, the amount you want, okay, into the water, right? Dissolve it completely, then put some more water in so that the volume comes up to the 20 mils that you wanted. Okay, you don't want to start with 20 mils because when you add in your metal nitrate, you know, your copper nitrate, it's going to raise the volume up, right? So you don't want to do that. You want to have less water. Then once you dissolve your nitrate, you can add the appropriate amount of water up to the 20 mils that you wanted, or whatever you want. You know what I mean? Then dry it, right? Dry it in an oven. And first of all, you want to stir it up, you know what I mean? Stir it up and dry it, okay? Now you have gamma alumina with your copper nitrate on it with a bunch of water. That's why you want to dry it. Get the water off, right? And once you get the water off, you just have your metal nitrate on gamma alumina. Then you just calcinate it. Calcinate it to the metal oxide, right? Heat it up. You'll have NO gases coming off, and heat it until it's all the metal nitrate has turned into metal oxide. Then put that in a furnace tube and hydrogenate it. You know, have some hydrogen going through. I'll get a video where some guy hydrogenates metal, and I will put a link to that in the description below, okay, so that you can see someone actually doing it. Because you can really blow yourself up hydrogenating metal if you don't do it right, okay? But basically, you just heat up the furnace tube with the metal oxide in it that's on the alumina, and the hydrogen will make sure that all the metal oxide turns into metal. Now you'll have metal on all the surface area of that gamma alumina. Now, I don't know how you do it with silicon dioxide, but I would assume that incipient wetness impregnation is done the same way as you do with the gamma alumina, okay? Now, the reason why you do this, okay, this method of making a metal nitrate and then putting it on the catalyst support structure, and then, you know, making the metal oxide, making to the metal, it's because, think about it, okay? If you just mix them up together like I did in the video with carbon and copper, it just gets the surface area. It doesn't get into the caves and the the holes that the catalyst structure support has, right? And it doesn't. And if you mix it, like I'm going to use chromium and copper, okay? So if I mix chromium and copper, is it going to be really mixed exactly good? No. But if I put it in water, if I put copper nitrate and I put chromium nitrate in water, the ratios I want, it will be evenly distributed, right? It's not like when you have ions in water that they have more ions in one part of the solution than the other. No, it's all smooth. There's just as much, it's spread across the water evenly, right? That's why you do this. And the other reason you do this, right, is not just to get everything evenly spread out. It's because the water will get into those caves and those holes and those crevices of the gamma alumina, right? And when you evaporate the water, the salt will be evenly distributed throughout not just the surface, but in the surface inside the caves and the holes of the gamma alumina, okay? And it will be perfectly distributed, all right? I myself am first going to start out with just plain copper. Okay, I'm not even going to jerk around with having a catalyst support structure. Because number one, the copper's better. Copper by itself is better. Okay, it's going to want to make acetaldehyde and that's it. You know what I mean? There won't be as many byproducts that I have to deal with, but it won't last as long. And when I say I'm going to use pure copper, I'm going to actually use copper with a little bit of chromium in it to cut down so it lasts a little longer. But if you really want your catalyst to last a long, long time, you do want to put it on a catalyst support structure. So sooner or later I will put it on a structure, but until I can get a better yield, I don't see the sense in it. But I will do it sooner or later. The last thing I'm going to go over in this video is how my apparatus is going to change, okay, because I'm not going to use the same apparatus I used in the video because I'm going to be putting the flow rate up high. Remember in the video I went really slow. This next time I'm going to do it super fast, and therefore I will need more cooling at the other end of the furnace to make sure that I don't lose any of the product. You know what I mean? So I will draw a picture of that and show you here in a second. Alright, my back is getting really screwed up, so I'm not going to draw a picture of it. But I'm just going to say that, coming out of the furnace, I had a first trap that had two condensers, right? The only difference I'm really going to make is I'm going to have maybe put a third condenser on there, and that's probably about it. We'll see how that works. But I'll just add more and more condensers until I don't have any overflow coming out of the bubbler that where I put the vodka in to collect. I will keep adding lengthening the condenser on that first trap until I can get everything out of there so it doesn't overrun the bubbler where the vodka is and go past that. I don't want it to go past that, right? Because that's where that's where I want it to all collect that. That was the problem I had. That was why I was going slow in the video here, because there was so much gases coming out of the furnace so fast that it couldn't all be condensed. It was going past the first trap, past the bubbler, and it just couldn't be contained. That was why I went slow in the video. But since I'm going to have to try to do it the correct way next time, I'm going to have to put more condensers or something on there so that it doesn't overflow the condenser and overflow the bubbler and get past it. So anyways, if you have any questions, please ask. I answer all questions. Anyways, you all have a great day, and always remember, science is great.